So, well, let's zoom. Standard, I guess, number 6. And this is a cardioid, right? So, coming back to this, well, we got that first part already, the graph. And, well, so express x and y as functions of theta. So in this case, one single r function will describe two functions x and y that will give the equivalent points in the Cartesian system. So number 1, in general, x equals r cosine theta and y equals r sine theta, where r is given. Let me color code by highlighting this. Okay, that's the function. Replace it here and there, and this will be x equals 2 times 1 minus sine theta cosine theta, and y equals 2 times 1 minus sine theta cosine theta. Okay, so this is what we're going to do. So number 1, let's see, okay, so that's the equation in parametric form. Yeah. Yes, that's what I meant, but not what I wrote. Thank you. Okay, so in this case, well, we could just take the derivatives and do the dy dx over the dy d theta over dx d theta. However, let's do step by step. So let's take the derivative of the x equation and the derivative of the y equation. So the derivative of the x equation, dy d theta, will be, okay, the derivative of the second equation. Be careful, we're doing the second first, and next we're going to do the first one. So in this case, to differentiate this function, we would need to use the product rule, because we have the product between 1 minus sine and sine. But I'm going to leave this coefficient of 2 outside. So, and then we will distribute it at the end. So what are we going to get here? So number 1, the derivative of 1 minus sine, the derivative of 1 is 0. The derivative of negative sine is negative cosine times sine. And the derivative of sine, which is cosine, times the derivative, oh wait a minute, yes, that times 1 minus sine theta. Alright, and then from here we can simplify. Well, that's a negative sine cosine, 2 times negative sine cosine, and cosine times 1, which is cosine, and cosine times negative sine, that's a negative sine cosine again. Alright, and well, combining terms together, we end up with 2 times cosine minus 2 sine theta cosine theta. And the last term is an identity. We can talk about this one when we're done with the example. So that's the derivative of the y equation. So this will be, well, product rule involved. Be careful, we're differentiating the first equation, not the second one. So the derivative of 1 minus sine is negative cosine times the cosine that we have over here, and then plus the derivative of cosine, which is negative sine, times 1 minus sine. So this reduces to 2 times, okay, I'm going to open parentheses here, and cosine, isn't that a negative cosine squared actually? And negative sine times 1, that's a minus sine, and negative sine times negative sine, that's a positive sine squared theta. Okay, so this simplifies to the following. That's okay. I'm going to write the sine squared minus cosine squared together. So that's 2 sine squared minus 2 cosine minus 2 sine. All right. So we have the two derivatives together. Now on the next page, they're asking us to find dy dx. Yes, so in this case, it's the expression that will give us the slope at any point on the polar curve, whether this is a cardioid, a flower, a rose. But in this case, that's going to give us the answer in the xy version. So dy dx, which is, by the way, dy d theta over dx d theta. So dy d theta, we got that is 2 cosine minus 2 sine theta cosine theta divided by, in this case, 2 sine squared minus 2 cosine squared minus 2 sine. And we can simplify this a bit by factoring out the 2's. Maybe we shouldn't have distributed in the first place, so we can factor it out. 2 cosine theta minus sine theta cosine theta over 2 sine squared theta minus cosine squared theta minus sine theta. Well, cancel out the 2's. They cancel, and we're left with cosine theta minus sine theta cosine theta over sine squared theta minus cosine squared minus sine. And well, this is an okay final answer. And in fact, I would recommend you to leave it in this form for further calculations. I will explain why in a second. But another version of this is if we replace with trigonometric identities. You know what? Never mind. Because I already looked. Never mind. That's fine. So, by the way, okay, let me go back a little bit. Because, okay, let me go back to the previous page. Because this negative sine cosine minus sine well, this was supposed to be a 2 here. This becomes 2 cosine theta minus 4 sine cosine. Okay, that's just a little mistake I did there. And okay, this is supposed to be a 4. When we factor out, this is a 2 here. So yes, we're going to go back to trigonometric identities here. So this is the actual final answer here. But an alternative version is cosine theta. This 2 sine cosine is an identity. That's sine 2 theta. And sine squared minus cosine squared. Well, actually, the backwards version, cosine squared minus sine squared, is cosine 2 theta. So because this is backwards, this is negative cosine 2 theta minus sine theta. So that's an alternative way to express this. You don't have to go the extra mile and express it this way. That's fine. And in fact, I wouldn't recommend that you do this, because when it comes to letter E, in which we are going to solve trigonometric equations to find the tangents. Well, not letter E, rather for letter F actually. So in this case, well, let's write the equation of the tangent line to the curve at theta equals to pi. Again, what are the two pieces of information that we need to find the equation of the line? Slope and the point, right? So we already have a derivative that we can use to find the slope. Great. Now we need to find the point. But where do we get the point? Where do we get the point from?
From the parametric equation.
From the original equation, right? The one that is described in parametric form that will output an x and a y. Not in the derivative, because recall the derivative will give us a slope. So let's see. So I'm going to go back to the original equation, x, y, the original parametric equation, which is 2 times 1 minus sine cosine theta, 2 times 1 minus sine theta times sine theta. We are going to evaluate this at theta equals to pi, and x equals to 2 times 1 minus sine pi. Well, I'm going to write it with a different color soon. Cosine pi, and y equals 2 times 1 minus sine pi sine pi. Okay, let's see. Let's simplify this. Okay, so cosine pi is -1, right? And sine pi equals to 0. Again, sine pi equals to 0. Sine pi equals also 0, which is great because the y value right here is going to be a 0. That's nice. And well, what we're going to get for the x value? Well, so 1 minus 0, which is just 1, times 2, that's 2. And cosine of pi, which is -1, that's going to become -2. So the point is -2, 0. We got the first part.
Why is the 2 negative?
Which one?
For the x values?
Oh, okay, so that's okay. Sine of pi, which is 0, 1 minus 0 is simply 1.
I have the
And then, so that's 2 times 1 times -1, which is the cosine of pi. All right, so the derivative, we're going to use the derivative to find the slope. So that is, okay, the derivative, which is this expression that we have from, let me write it as dy dx, all right? So we are going to evaluate dy dx at theta equals to pi. So again, this will be cosine pi minus 2 sine pi cosine pi over sine squared pi minus cosine squared pi minus sine pi. Let me write the pi with a different color just so we can see how we evaluate this. And let's see. Let's just compute all this. Unit circle, or you memorize this. One's cosine of pi, -1. Sine of pi, 0. Doesn't matter what cosine of pi here is. It's going to be multiplied by 0. So sine pi, which is also 0, square it, 0. And cosine pi, which is -1. But that -1, keep in mind that it's being squared because of this exponent. -1 squared will be +1. But be careful because we have a negative in front of it. Alright, well, so let me call this first a +1, which will be affected by the negative later on. And negative sine pi, that's a 0. Okay, so what do we have? -1 minus 2 times 0, which is simply 0, and we have 0 minus 1 minus 0. That's going to be 1, which is the slope. And finally, we have both pieces of information that we need to find the equation of a line that is tangent to that cardioid when the angle is theta equals to pi. Well, what do we do? As usual, y minus y1 equals m times x minus x1, where y1 is 0, m, which is 1, times x minus x1, which is negative 2. Be careful with the signs. This will be y equals to x plus 2. All right? Okay, so here is the thing. I don't want to just give you this experience that we're only crunching numbers and symbols, derivatives. What's the whole visual here? Well, we're getting the equation of a line that is tangent to that cardioid, but how do we graph these two together? Because something to keep in mind, we already plotted the cardioid, but we use the polar form. But this equation y equals x plus 2 is not in polar form, it's in Cartesian form. So we cannot plot one equation in one system in the calculator and then another one in the other system. So we would be having to switch between modes. So let's do the following then. Let's change this equation to polar form. This is r sine theta, r cos theta. So this will result in r sine theta equals r cos theta plus 2. Let's have all the r's on the left hand side and then everything else on the right hand side. R sine theta minus r cos theta. Well, I know we're still crunching symbols anyway, but at least we're going to do this so we can get the picture, literally. So r equals 2 over sine theta minus cosine theta. Alright, so that's the equation in polar form. And we may now go back to the picture, to the graphing calculator. Okay, let me do some zoom fit perhaps. No, maybe a little bit less. Zoom out a little bit. Well, it did a lot of zoom. Anyway, so on an R2, let's type the equation that we just found. But be careful. Okay, be careful when typing these equations. Think of all this having parentheses, because, well, we need to put parentheses around those on our graphing calculator so we can indicate the calculator that everything is in the denominator. So that's a sine theta minus cosine. Oh, that's not the correct syntax. And minus cosine theta and close parentheses. Now when we hit the graph button, look at that. This is just to show the consistency of the calculations that we are doing. How we're finding the equation of a tangent line. Same process. Yes, it's a different world. It's the polar world. It's different type of calculations, but ultimately stems from the same concepts in just a different way. All right. So this is really the bigger picture of what we're doing. For letter F, I think